Alright, we are continuing our review of exponential and logarithmic functions. In this video, we will focus on solving some word problems, some real-world problems involving exponential and logarithmic functions. A lot of things in math, students will ask me, well, when is anyone in life ever going to use this? And I don't always have a great answer depending on what we're working on. When we work with imaginary numbers, I can say something about electricity and electrical engineering, but it's really hard for me to communicate where imaginary numbers show up in the real world. They do have a purpose, by the way. It's just hard for me to communicate what it is. But when it comes to logarithms and exponential functions, that's not the case. There's a very clear use of logarithms. They come up in business, finance, economics. I use this in day-to-day life. If I want to figure out how long it's going to take me for my investment to reach a certain amount, am I going to be able to save enough for college, in the time I've got before my kid turns 18, you're going to need exponential and logarithmic functions. So this is good, useful stuff. Let's take a look at number 3. You deposit $1,500 into an account that is compounded continuously for 18 years. Alright, let's pause right there. We've got these 4 different functions that pertain to exponential growth and exponential decay. 2 of them are all about compound interest. So that's this function and this function are specifically for compound interest. So half the battle is knowing which formula you're supposed to be using. So since both of these are compound interest, alright, compound interest. So how will we know which one of these to use? Well, this one over here on the right is the one we use when we are compounding continuously. Okay, and this one on the left is when we compound in any other interval, whether it's daily, monthly, what have you. Okay, so as soon as you see compounded continuously, that lets you know that we're going to be using this PERT formula right here. Okay, so when we write the model for investment, we're looking at the PERT formula, and we know that the amount is going to be, now P stands for the principal, so that's the initial amount of $1,500. And then E is a constant, and then that's to the RT power. Okay, we don't know the rate, so we're going to have to leave that as R. But we do know the time, the T, is 18 years. So I'm just going to put 18R. Okay, so this would be the model for this investment as a function of rate, the only thing we don't know. So if you want to have $20,000 in 18 years, what interest rate must the account have? So where does this $20,000 go in the formula? Where it's obviously not the rate. In fact, it says what interest rate, so we're looking for R. So it must go here, which makes sense because this is the amount that we're going to have, sometime later, 18 years later. So putting the 20,000 right here, we have 20,000 is equal to 1,500 times e to the 18r power. So it's just a matter of solving this equation for r. So your first move should be to divide both sides by 1,500. Okay, so 20,000 divided by 1,500. Okay, that's 40 over 3. And I don't want to round, so I'm going to leave it like that, 40/3. Alright, if you can avoid it, you should try not to round until the very, very last step. If you do have to round mid-problem, carry 4 decimal places until the end. So anyway, we have 40/3 is equal to e to the 18r power. So if you want to get the variable out of an exponent, that's what logarithms are for, because logarithms are exponents. In other words, let's go ahead and rewrite this in log form. Now, if you were not careful, then the first thing you would write when you write log form is normally we write log and then the base. So we would have log base e. Now everything else switches sides. So the 18r and the 40/3, these trade places. Okay, so the 18r would come over here and the 40/3 would come over here. Now I said you would write this if you were careless because we don't write log base e. Alright, there's something special we write when it's base e. That's the natural log. So instead of writing log base e, we write ln for natural log. So we'll have natural log 40/3. So this is what you should write. So you really would skip this step. I'm only showing it for instructional purposes. So it's just a matter of solving this now. So we're trying to get r by itself. So all we have to do is divide both sides by 18. Okay, so that's going to give us the rate. So we just need to do natural log 40/3 divided by 18. Okay, so we'll have natural log 40/3 and then put that over 18. Okay, so as a decimal I have 0.1439 and keep all 4 of those decimal places. Okay, so when you are giving the rate, you're going to want to always give the rate as a percent. So you're going to need all 4 of these decimal places because when you turn it into a percent, you really will only have 2 decimal places. So this will be 14.39%. Alright, these both mean the same thing, but again, if you have it in decimal form, you need 4 decimal places, not just 2. Alright, in other words, it's not okay just to round this to 14%. It's got to be 14.39%. Alright, let's look at a few more examples. You buy a new car for $27,000. The value of the car decreases by 13.5% each year. Let's write a model for the value of your car over time. So a model just means an equation with the variables in there. So let's look back at our options. This is not compound interest, so we're not going to use either one of these two. So we're talking about either general growth or general decay. Since this is decreasing, it's going to be decay. So it'll be 1 minus the rate instead of plus. So the model that we're talking about is the value of the car is going to be the initial value, which is 27,000, and then it's going to be 1 minus the rate. 13.5% as a decimal, you got to move this twice, so that's 1 minus 0.135, okay, to the power of time. So this is the model. Now we tend not to leave this as 1 minus 0.135. It's traditional to go ahead and do this subtraction. So 1 minus 0.135 is 0.865. Okay, this is our multiplier. So I encourage you to go ahead and rewrite it and put 0.865. Okay, so this is the model for the value of the car over time. Now, when will the car be worth 1/3 of its original price? Okay, well, its original price is $27,000. So 1/3 of that, 27 divided by 3 is 9. So it will be $9,000 when it is 1/3 of its original price. So we are asking, when will the value drop to $9,000? So if this value is 9,000, then we have 9,000 is equal to 27,000 times 0.865 to the t power. So the when is this time, and we're just solving for it. So your first move should be to divide both sides of the equation by 27,000. Okay, but of course, if you do 9,000 divided by 27,000, we're going to get 1/3. All right, that's why we picked 9,000 in the first place, is because it has to be 1/3 of its original price. So that's going to give us 1/3 is equal to 0.865 to the t power. Now, if you want to solve for an exponent, the best thing to do is use log form, because logs are exponents. So if you rewrite this in log form, then we always start by writing log base. Now our base is the 0.865. So we have log base 0.865. Everything else changes sides. So the t and the 1/3, we're going to change sides of the equation. So the t is going to come over here, and the 1/3 is going to be right here. So we can evaluate this using the change of base formula. So that would be log of 1/3 over log 0.865. Okay, so log of 1/3 over the log of 0.865. Alright, so that is 7.58. Got to round up. Okay, so we're talking about years. So that is the answer to the question, when will the car be worth 1/3 of its original price? That'll be a little over 7.5 years after you bought it. Okay, a couple more examples. Alright, let's look at this fictitious country called Ugabuya. It had a population of 2,300,000 people in 1985. Since then, the population has increased at a rate of 2.4% per year. Write a model to estimate the following information. Okay, so as far as the model, obviously this is not compound interest. So we're talking about either general growth or general decay. This population is increasing, so we will use the general growth model right here. So looking at that model, then the general growth model is going to be y equals, and then it will be the original population, so 2,300,000, and then it will be 1 plus the rate. So I have 1 plus, and 2.4% as a decimal, you have to move this twice, so that would be 0.4 0.024, and then to the power of time. Now again, for the multiplier here, we don't tend to leave this as 1 plus 0.024. We go ahead and do the sum, which we can do in our heads. That's just going to be 1.024. Okay, so for the model, please do not put in any value for t. Alright, now for part B, find the current population. Now here it says 2014. Should probably change this because now it's 2015. So as we estimate the population in 2015, remember this original population of 2,300,000 was from 1985. From 1985 to 2015, that's 30 years. Okay, so we're talking about t being 30. So you could just type the whole thing in your calculator, substituting 30 in for t, and this is what we get. So, alright, let's be careful about the decimals here. So we have 1, 2, 3. Alright, so we're talking about 4 million. Let's round this to the nearest person. Okay, so let's round, this will be rounded up to a 3. Alright, because that's a 7. So it's 4,685,183. Okay, so that's the answer to part B. Now, when will the population reach 3 million? Okay, well, the population already reached 3 million, but when did that happen? Okay, so we're already up to 4 million in 2015. Okay, let's see what t value that was. So if we substitute 3 million in for y, then the model becomes 3 million is equal to 2,300,000 times 1.024 to the t power. Okay, just using our model. Alright, so it's just a matter of solving this for t. So your first step should be to divide both sides by 2,300,000. Alright, that'll cancel those out. So let's see. Okay, so this is 30 over 23. Okay, let's leave it like this. Let's not make it into a decimal. If we make it into a decimal, then we have this ugly thing. We're going to wind up rounding it. If you have to round and it's not the end of the problem, you need to carry at least 4 decimal places. But it's a lot neater just to use 30 over 23 anyway. Okay, so this is equal to 1.024 to the t power. So it's just a matter of solving this for t. So if you want an exponent, use log form. So if I rewrite this in log form, then on the right hand side I'm going to have log base, and this is my base, so log base 1.024. Now the rest of this, the t and the 30 over 23, are going to change sides of the equation. So the t is going to wind up over here by itself, and the 30 over 23 is going to wind up over here. So I can evaluate this using the change of base formula. So I'm going to do log of 30 over 23 over log 1.024. Okay, so log 30 over 23, whoops, okay, over log 1.024. Alright, so that gives us 11.20. Okay, and this is years. So a little bit over 11 years. Okay, so 11 years after 1985, which is when this all began. Alright, so 1985. Okay, we're talking about 1996. Okay, so a little ways into 1996 is when the population would hit 3 million. Alright, so that is the answer to number 5. Okay, let's see. Alright, we have two more examples. Alright, look at number 6. You deposit $7,000 into an account that earns 5.6% interest compounded continuously. Alright, as soon as we see that word continuously, we know that we're going to use the PERT formula. Okay, so the amount is going to be P times E to the RT power. Alright, that's the formula for continuously compounded interest. So, alright, so as far as a model, that means the amount is going to be $7,000 times E. Now the rate is 5.6. Got to move that decimal point twice, so that's going to be 0.056 and then T. Okay, so this is the model for this investment. So for part B, how long will it take for your investment to double? Alright, round your final answer to the nearest hundredth, so that'll be 2 decimal places. Well, if our investment is going to double, that means it's going to go from $7,000 to $14,000. So this model is going to become $14,000 is equal to 7,000 times e to the 0.056 t power. So it's just a matter of solving this for t. So again, your first step should be to divide by that 7,000. Alright, and no surprise, this is going to turn out to be 2 because it doubled. Of course it was going to be 2. So we have 2 is equal to e to the 0.056 t power. Now, so it's a matter of solving this for t. If you want to get at the exponent, you're going to need log form. Now, if you were careless, you would start off by writing log. And because log form, we have log and then the base, and then everything else changes sides. So this is going to go to the left, and this is going to show up on the right. So over here on the left, I'd have 0.056 t. And over here on the right, I'd have log base e of 2. Now I say if you were careless because log base e is special. We don't write log base e. That is the natural log. So you should write 0.056 t is equal to natural log, ln, natural log 2. So if you want to get that t by itself, all you have to do is divide by 0.056. Okay, and there you go. Just put that in your calculator. So natural log 2 over 0.056. So natural log 2 over 0.056. So that is 12.38. Got to round up. Okay, and we're talking about time in years, so this is years. So that is the answer to that question. It would take a little over 12 years for your investment to double at this rate. Okay, let's do one more example. Number 7. You deposit $6,000 into an account that earns 10.2% annual interest compounded quarterly. Now, quarterly means 4 times a year. So it's time to use the other formula, which looks like this. This is the formula that we use for compound interest when it's not compounded continuously. If it's daily, monthly, quarterly, anything like that. And the n represents the number of times a year that you are compounding. So if you're compounding monthly, n would be 12 in both positions. Daily, alright, that's 365 times a year, so that n would be 365. But for quarterly, quarterly means every 3 months, 4 times a year. So n will be 4. So we're just going to do this model. Okay, so keeping an eye on this model, the $6,000, that's the initial investment. That's called the principal. That's P. So our amount sometime later is going to be 6,000 times 1 plus the rate over the number of times a year that we compound. So 1 plus, now this rate, 10.2%, as a decimal, we move the decimal point twice, so this will be 0.102. Alright, over 4. Again, that 4 is because we're compounding quarterly, n is 4. Okay, now then it's supposed to be to the n times t power, so that 4 is going to show up again in the exponent, and then t. Alright, so this would be the model for this situation. Okay, now we're going to use that model to figure out how long it will take for our investment to triple. Alright, well, if the investment's going to triple, it's going to go from $6,000 to $18,000. So putting $18,000 in for the eventual amount that we will have right here, then the model becomes this. So if I want to know how long it will take, then I'm solving this equation for t. So once again, our first step will be to divide by this principal. So divide by 6,000 on both sides. No surprise, this turns out to be 3 because we were answering the question, how long will it take for the investment to triple? So of course it was going to be 3. So 3 equals 1 plus 0.102 over 4 to the 4t power. Okay, now this is the one time I'm going to go ahead and round ahead of time. I'm going to have to rewrite this in log form, but writing log base 1 plus 0.102 over 4, that's going to be very cumbersome. So I'm going to go ahead and turn this into a decimal now. But I'm going to say this twice. Keep 4 decimal places because it's not the end of the problem. So let's see, let's find this decimal. So 1 plus, and then I had 0.102 over 4. Okay, so that's this. Oh, you know what? The 4 decimal places, that's this whole thing anyway, so I don't have to actually round. Great. Alright, so 1.0255. Do not round this. Don't put 1.03 or anything like that. We need all of this all of these decimals, all of this accuracy. 1.0255. So we have 3 is equal to 1.0255 to the 4t power. So to get the variable out of the exponent, I need log form. So if I rewrite this in log form, okay, then I'm going to have log base. The base is this number, so it's log base 1.0255. Do not round this. Everything else changes sides. So the 4t and the 3 change sides of the equation. So the 4t is going to wind up over here, and the 3 is going to end up here. Okay, so to get t by itself, I'm going to have to divide both sides by 4, like this. Okay, so now I'm going to have t equals. So it's just a matter of evaluating this. Now, when I put this in my calculator later, I'm going to have a very compound fraction here, because the blue part, when I do the change of base formula, it looks like this. It'll be log 3 over log 1.0255. Okay, but then all of that is supposed to be divided by 4. So I'm supposed to take this entire thing and divide that by 4. Okay, now I can put this in my calculator easily, but many students get confused and wind up typing the fraction in wrong. So I'm going to show you how I would type it in as a compound fraction, but then I'll show you how to type it in if you're the least bit uncomfortable. Okay, so first of all, I would just go into fraction mode immediately. Now, looking at the larger fraction, the blue over the pink. Alright, this pink number 4 is the denominator. So you can go ahead and put 4 in the denominator right now, get that out of the way. Now the numerator is itself another fraction, the blue. So in the numerator, I can hit the fraction button again, and now I have a fraction in the numerator. So that fraction is log 3 over, okay, so I have log 3, and then that's over log 1.0255. Yeah. Okay, so that's how you would type this in as a compound fraction. And then you can just hit enter and get your answer. So it's 10.91. Got to round up. Okay, 10.91 years. Now, if you're uncomfortable typing in that compound fraction, you might type it in this way. Just type in the log part. Okay, this part here in blue. Type that in. Don't type in the divided by 4 part yet. Okay, just do log 3 divided by log 1.0255. Okay, so that would look like this. You could go ahead and hit enter and get this decimal. Now you know that we have to still divide by 4. So you don't need a round or anything. You can just go ahead and now hit divided by 4. So that gives you the exact same answer that we got when we typed it all in at once. Alright, 10.91. So most students are more comfortable doing it this way. Okay, alright, that's going to be it for this video. I hope it was helpful. On the next video, we will do more practice with solving exponential and logarithmic inequalities. But this time, we're not given the graph, so we won't be able to use that particular shortcut. We'll have to do it out the long way.